Sam's going to help you out for now? I'll come back to you. Yeah. Okay. So, whoa. Oh my gosh. My poor board. It's having some issues. If I were the solution to this problem. Solution. What's wrong with solutions? I might have to do this stupid thing again. Okay. Okay. Dissolve. Ooh. And solution. That's pretty much what I like. Okay, that's simple as you can get. As temperature increases, the solubility of solid and a liquid. So solubility of solid generally does what, Alex? Increases. Right. Usually you increase the solubility of something when you increase the temperature if it's an ionic solid. So those are generally relationships we should know. Increase in temperature does what to the solubility of a gas? Darian. Yeah, decreases the solubility of a gas with increasing temperature because kinetic energy, right? Increasing kinetic energy, it's able to evaporate faster. As the pressure on the surface of a liquid increases, the solubility of a gas in that liquid does what, Josh? Think of our examples yesterday of the soda bottles. Okay, good. So you're increasing the pressure above the liquid, like carbonated soda. Increasing the pressure kind of pushes the gas molecules back into the soda, so it's more soluble. You've got more gases dissolved in that liquid. So increasing pressure increases solubility of a gas only. Sorry, you guys know my handwriting wasn't fantastic on the board to begin with. This little marker thing is fantastic. Okay, so let's go back here. Using our graph, what was the process of how you walked yourself through this? Aaron? Okay, so, but what, we see that this is temperature dependent, right? All of this solubility stuff is temperature dependent. Nathaniel, pick up.
80.
Tell me your process. I don't care the answer right now.
You follow the line from K and 3 down to 52 Celsius.
Okay, so you went, 1 second, hold on, walking through there. K-3 is here. It's this big, huge, long line. And you drop down to see the 50-degree mark, which was here. So where do they meet?
You follow it up with the line, and wherever it meets from the pressure, it's already
Sorry, Alex is calling me. It's 7 o'clock in the morning. Okay, so it's 80 grams for what?
Well, it says it's 87.
Oh, but there's a process here, right? So we have an axis that tells us some units. Why is that important, Darian? Right. So 80 grams of KNO3 per 100 grams of water. What was the question? In 200 grams of water, how much is dissolved? So the answer is not 87. The answer is 160 because it's a ratio. 80 over 100. And then for the 200 grams of water, you double the solute and the solvent. So 160 grams of potassium nitrate will dissolve. Okay? So I'm going to probably ask you a question just like this on the test. Okie dokie? So let's talk about molarity today. So I'm not going to go over the molarity worksheet. I saw a lot of us that did not have it done. So if you had it done, I'll see it today. I'll give you your full credit tomorrow. I'll take it as late credit. So have it on your desk for me. I just have to come around and check it as we go. So we're going to talk about differences between solutions talking about number form and solutions talking about qualitative forms about dilute and concentrated. Then after that, we'll do a lot of practice problems in class. So what I'm doing is I'm going to do about 20 minutes worth of examples and talking about molarity versus molality. We'll practice for 20, 25 minutes, and then we'll finish up next. So that means you have time to ask me questions in class per your request. So let's see how this goes today. So this is basically a quick review of yesterday's molarity worksheet. So I'm not going to spend forever here because some of you guys are going to be like very knowledgeable about it. If you ever have a concentration or you're talking about a solution, you always have a solute and a solvent. So the solute and solvent are related through a ratio. We call it their concentration. So if it's a lot of solute in the solvent, it's fairly concentrated. There's a lot of stuff there. If there's a little bit of solute in the solvent, it's fairly dilute. There's not a lot of stuff there. So that's basically our relative comparison. So dilute versus concentrated is only a relative comparison. There's no quantity given. We're just like, oh, there's more in this one, there's less in this one. And my best example is going, if you guys talk about fossils, and you have layers of rock, and you've got 5 layers of rock, which is the oldest layer? Concentrate, because relatively it's lower, but you don't know if it's 10,000 years old or 100,000 years old. You don't know the number. It's just like, oh, this one's older than this one. So that's what we say about dilute versus concentrated. So we're always talking about amount of solute and amount of solvent. Or sometimes the whole shebang. Sometimes we have to consider the sum of the solvent and the solute, but it's just depending on what we're talking about at that given time. So quantitative means, use a number. We have a quantity, a number associated with it. And for us, we generally use molarity. We're familiar with molarity. We've worked with it before. Generally, we use molarity. We also will be using something called molality. What's the difference between these two words? The R and the L, right? Really easy to mix up. We're going to hit molarity a lot.
Pardon interruption. This is just a reminder for teachers with first period planning to report to the PC lab at 7:30. All teachers with first period planning report to the PC lab at 7:30.
Okay, so the biggest difference here is going to be between their units, and we're going to talk about that today. Okay, so this is just intro. So, oops, I accidentally skipped a slide. Sorry. I'm going to go here first. Molarity. So molarity is going to be our big one, and we already are fairly familiar with what it is. It is, if you don't write anything else, at least write this, moles of solute over liters of solution. Solution is equal to solute and solvent. But usually we're given that value because it's hard to always add them up or calculate it ourselves. So this mathematical way of writing it is the same as the definition. You do not have to write both of them. Like I said, this is quick so we can do practice today. That blue part right there, where it says intensive property, that's basically saying, if I have some Kool-Aid, and I have it in a big 2-liter bottle or big jug, right? Let's say it's 5 molar. And then I pour it into a glass for me, and a glass for you, and a glass for you, and a glass for you. Is the concentration changing as I pour it into the glass? No, it's still, like, that would be disgusting if it was like, oh, we have nice tasty Kool-Aid, and then you pour it into a glass and it's like, ugh, gross, it got diluted all of a sudden. No, you're not adding water. You're not diluting. It's the same concentration. So it doesn't depend on the amount. You can have a whole 1 million liters of this substance, and it's still 2 molar sodium hydroxide, or you can have 1/2 of a liter of it, and as long as the moles, the ratio is not changing, it's still 2 molar. It's just saying it's not dependent upon the volume you have. So let's do this example question. And what I said for example questions, I'm going to scroll real fast. This is our general
Teachers, pardon
flow.
interruption again. Teachers, this is just a reminder for all planning periods to report to the PC lab 15 minutes until that period. Thank you.
Okay. So you're always going to write down your knowns. You're always going to, at least for problems like this, think about the units you want. If I ask for molarity, what units do I want? Moles of solute. So you got to think about who's a solute over liters of solution. Okay, so you got to really think about the units and put them on top of each other. And then think about, like, does this make sense? Does the amount of the stuff I have make sense? So we'll get really good at finding our logic here. Okay, so for this first example, I'll do a couple lead ones with you, and then you guys can do some by yourself. What's the molarity? So stop here. What am I looking for? Right, moles of what? What's the solute in the question? No, who? Sodium chloride, okay. We're looking for moles of sodium chloride over liters of solution. SOLN is how I write solution, you probably figured that out. Okay, so now I can continue. So basically, I usually define what I'm looking for first, because sometimes it's more complicated with these ratios. So you have a 5-liter solution. It contains 4.3 moles of sodium chloride. This one's easy. What do? 4.3 moles of sodium chloride over 5.00 liters of solution. And then I just divide, right? Okay, so what's the final answer? I was looking for my notes, but I'm just going to repractice it. What is it? 0.86, thank you. How many sig figs do I need? 2, so that's good. 0.86, big M is molar, right? So 0.86 molar is what that concentration is. Easy peasy, yeah? Thumbs up when you're ready to go. All right, so I'm going to start you off with different givens. So I gave you literally the moles and the liters, and we just divided. So what else could I start you off with? Grams, and I could ask you to get to moles, right? Or I could ask for a different part of the question. I could say, if I have this molarity, how many grams did it take to make it? So we could work backwards. So you can see there's probably 5 different questions, question types. But if you always start with the same givens, figure out what you're looking for, you'll be fine. So a saline solution contains 0.9 grams of sodium chloride per 100 mils of solution. What is the molarity? So again, what are we looking for? Moles of who? We're looking for moles of NaCl over liters of solution. Good. What are my givens? I'm starting with grams, right? So tell me what I'm doing. Loud and proud, you got this. 0.9 grams of sodium chloride times of sodium chloride over 58.44 grams. So that's just 23-ish plus 35.45 for chlorine. So that is, anybody? 0.015. 0.154. I'm going to expand it out just a little bit, and it's zeros after that, just so I don't have any rounding error. All right, so there's how many moles I have. Now what? Okay, so I need to convert this to liters. I don't have to show my work for that. How many liters is that? How many? 0.1. So it's just moving the decimal back. 1, 2, 3. So that's 0.100 liters of solution. All right, so the two values I care about are here and here. Now what? Divide. So if you just want to circle your two givens and then show me your dividing, or, you know, some of this work is necessary. Showing me your liters is necessary, and then maybe showing me your setup here with your final, you could skip. But the more work you show, the less mistakes you make. So I'm just trying to protect you from yourself here. So that is 0.154. How many sig figs should I have? 2. Good, because you've got 2 sig figs here. So this needs to be rounded to what? 0.15 molar NaCl. Because you always identify what it is if you can. And we can here, it's sodium chloride. Thumbs up when you get to move on. Okie dokie. So I'll probably do 1 or 2 more of the molarity. So let's look at this one or this one. Let's see, I've got 3 more. Let's start with this one. We'll work backwards if we need to. All right, so question. What's our question? Grams of lithium chloride would you add to make 2 liters of a 2.5 molar solution? So our two givens are, we have 2 liters, and it's a 2.5 molar solution. Think for a second how we can get to some useful, yeah.
And it needs to be like 2.5 molar equals however many moles over 2 liters.
You could set up a proportion. That would get us to moles, and then you can get to grams. I prefer to just like write out the work that you would be doing, because you know you set up a proportion, and then what are you going to do? Right, so you're going to be multiplying liters by molarity. So why don't we just do that? Right, so I tend to just go straight to the math. You guys can set a proportion and then go to the math. So basically, if you, and I told you guys this way a long time ago, if I ever give you molarity and I give you volume, what do you do with them? and that gives you moles. Do you remember that? So you remember molarity is just moles per liter. If you multiply by liters, what cancels? So then you are stuck with moles. Well, that's a great unit to be stuck with, because then what's my final conversion? Molar mass to get to grams, right? So I like what you said, proportion, and I'll write that here, but you'll never see my work as a proportion. Just BT dubs. So 2.5 moles per 1 liter. That's assuming you know how to transform this into this. And then she said, okay, question how many moles over 2 liters. Well, you should be able to tell me right now. 5, because it's just double. Double the solution, doubles the moles, so it should be 5 moles, which is, I can prove to you here, is 2.5 times 2, 5 moles. Okay, 5 moles of what? Lithium chloride, good. So this, I'm going to kind of just give me a squiggle here. 5 moles of lithium chloride times its molar mass. So I'm going to put 1 mole in the bottom of lithium chloride. What's the molar mass of lithium chloride? 44 what? 0.2. I can't erase, dang it. 42 point, thank you, 39, I think is what you said. Grams of lithium chloride. Okay, so then you take 5 moles times the 42.39, and Aaron, what'd you get? 212 grams of lithium chloride. Okay, so step back and see if this makes sense, right? We have, in 2 liters, we have 5 moles of lithium chloride. Lithium chloride is about 50 grams, about. So if you have 2 liters of it, this is about 50, I'm sorry, you have 5 moles of it in 2 liters. 5 moles of it by about 50 grams, that's about 250 grams, right? So I overestimated, so that's about right. Okay? So you can always kind of step back and make sure you did your math right. Can I go past this one? Let's do one more. Tell me which one you want to do. Oh, we haven't done with volume. Like, I think I want to do that one. Yeah. Let's do a hard one. Okay. What would the final volume be? So question. Volume. Be of a 0.75 molar solution of, what's the name of that? Aluminum nitrate, if it contains 280 grams of aluminum nitrate. So I know I have to use the 0.75 molar someplace, and I know I probably should be using the 280 grams of aluminum nitrate someplace. Okay, so if I convert, and let me point out something. Molarity, it's a conversion factor, right? Because it's a fraction. It's moles over liters. And for conversion factors, do they have to stay as is, or can they be flipped? They're up to you, right? Whatever you want to do with them, manipulate them. So I'm going to put CF there to remind you it's conversion factor. So yeah, you're right. You want to take your grams first to moles. That's usually the best step. 1 mole, nope, I lied. 1 mole of aluminum nitrate weighs how much? Sorry, my notes are hidden away from me. There they are. $213-ish. Is there a decimal? 0.01, okay. Grams of aluminum nitrate. Okay. Now, right now I'm at moles, right? I'm 2 moles. I can stop here, get moles, and then move on to find the liters. But we should be okay with proceeding with the conversion factor, like doing one big stretch of math. And if not, stop here, get your moles, and then go further. Huh? Can we just keep going? Let's just keep going. So let's just take our grams, cancel them. We have moles. What's our question again? So what unit are we looking for? Liters. Is there a way to get liters on top with the rest of our information? Yeah? So take this and do what? So what am I writing? 1 liter of solution on top and good. Of aluminum nitrate on bottom. So moles of aluminum nitrate cancel. basically molarity is, 0.75 moles of aluminum nitrate over 1 liter of solution. So we just flipped it to get liters on top, which is the easiest step to do. Okay, so then you would just calculate across, you get your liters of solution, which I don't have in front of me still, for some reason. It's useless. Okay, so let's try to do molality now. Molality, ready? What's the answer? You have that, Aaron? 7.5, I think. So we would actually want to convert that, truncate that at 2 sig figs, so 1.8 liters. Sig figs. Okay, so molality, and then I'll give you guys some time to practice by yourself. Molality, what's different based on what you're seeing here? I know the L and the R is different, we got that. Okay, but what else is different? So instead of being liters in the bottom, you can see it's kilograms in the bottom. Kilograms of solvent. What was molarity? Solution, the whole shebang, right? Now we're specifying just the solvent. This is very, very different. So put a star or something to go, like, watch yourself, don't get messed up. What else is different? It is still number of moles of solute. That's still the same. How do we denote molarity versus molality? What letters do we use? Lowercase m, right. So this one's got a lowercase m versus capital M. So if I write little m next to something, I'm telling you, if I say 5 little m, 5 molal, or so let's go with this one, 2 molal sodium hydroxide, I mean 2 moles of sodium hydroxide over 1 kilogram of solvent, which is probably water. Most of the time our solvent is water. Okay, so let's practice. Oh, and so the last one, we had volume, changing volume, never change the concentration. This one can change with volume, because if you have a different volume of solvent, you've got a different whole number. So that's why it is dependent upon volume. Okay, so let's try a practice one. What is the molality? So what am I looking for? Specifically, what am I looking for? Of, who's a solute? Over. Okay, I'm going to put kilograms of solvent, which is water here, and you can put 1 there, but we're, in the end, we're going to be dividing by number and then solving for it to be over 1. So we're looking for this. What are you going to start with? Change it to moles. 55.4 grams of potassium nitrate, 1 mole of potassium nitrate. And I don't know if you guys realize this, when you guys are responding and like calculating and getting the answers and stuff, things go faster versus us waiting on the whole class. So it's in your best interest to participate so you can have time for homework. So what's the molar mass of potassium nitrate? What is it? 101.1 grams of potassium nitrate. Okay, so then how many grams is this? Should be about half a mole. Half a mole. I can't remember what I just said. What is it? Is it 55.4 what? 548. 0.548 moles of KNO3. Okay, now what? Grams and kilograms, right? Can we do that in our head? How many grams? How many kilograms is that? 0.300 kilograms of water. Okay, so we got 0.3 kilograms. We got this many moles. Now what? Divide. So 0.548 moles of potassium nitrate over 0.300 kilograms of water gives us what molality? Anybody? Okay, 1.82 molal. Little m. Yeah, 3 sig figs all the way. Yeah.
Doesn't the bottom have to be 1?
Well, when we divide and we divide these numbers, it comes out to be this many moles of potassium nitrate over 1 kilogram of water. When you divide this ratio here, it gives you this. So instead of writing all that mess out, we just write it as 1.82 molal. Not liters, because that's molarity. We're talking about molality now. Okay, moving on. Let's do another one. Oh, no. Oh, yeah, sorry. No, I want to stop this now. We'll do some more in a second, okay? So I'm going to, this is my joke for you. I have to show you something with stoppers. I want to tell you in a second. Okay, so, ooh, that hurts. Oh, shut up. It's all in the name of science. In the name of science, take $5 and clear out. This is 5 molar. Your teeth. It's 5 molar solution. Sorry, that was a little lame, but you know, I tried. Okay, so you guys have these practice problems on your sheet. You have your little worksheet I gave you yesterday, and it says back, so turn on the back. Because it looks like there's only 4 examples, but there's 16. Okay, so 18. We're going to do probably about, let's see, how many is this? 10? 1, 2, 3, 4, 5, 6. I know you can do the first 6. We just went through tons of examples about them. And then I know you can accomplish right now 10 through 13. The other stuff we're going to talk about in about 20 minutes, okay? So right after 8 o'clock, I'm going to start writing up notes. Right now is your time to practice with a partner, with me, ask questions. The more you get done, the less homework you have, okay? So you'll be finishing 1 through 18. I mean 18. So I'm expecting you'll get about 10 done right now. Let's meet the expectations. And thank you, Erin, for being my calculator. I'll give you some mole money because you're like the only person that participated right now. Preach. I owe somebody else more money. You can accomplish right now 1 through 6 and 10 through 13. Because that's what you know right now. You don't know how to do 7, 8, and 9 and the other ones just yet.
Oh, yeah. What is this about?
That's from yesterday for helping out in class.
Okay.
All right, so show your work. Please, please, please. Show your work. All right, so the dilution equation is simply a way to take a really concentrated solution and show how to take it down to a more diluted version. Well, heck, most of the time when we dilute stuff, what do you think we're adding to it? Lots and lots of water, right? That's generally what you're going to be seeing in all of these questions. But the amount of water will matter. So I can't just go lots of water is added. I have to say 35.45 milliliters of water is added. So we got to quantify it, right? So what is this big M standing for? Molarity. What do you think the V is standing for? Volume, okay? So we must have, when we're talking about 2 different solutions, we label them 1 and 2, just like we had on our P1V1 equals P2V2, 2 different scenarios. Let's put the same thing here. Generally it doesn't have to be. This M1 and V1, we'll be talking about the stock solution. Stock solution is basically I have behind in Narnia back there, behind the room, I have a stock room. Stock rooms have really, really concentrated acids, bases, solutions, stuff I would never put out here because it's just dangerous, right? So most of the time when I make solutions for you guys, I go to my stock room, I get my concentrated 14 molar hydrochloric acid, and I dilute it down to 1 molar hydrochloric acid, something much more diluted so we don't, kill ourselves and burn our eyes out or something, right? I like you guys a little bit, so. This right here is going to represent what I've done, my diluted version. So generally, my M2 and V2 is regarding my diluted stuff. Doesn't have to be, but that's kind of the general scheme I'm going to stick with. So I will probably give you, oh, you got a 14 molar HCl solution, and I want you to dilute it down to a 1 molar HCl solution. And then you go, well, how much do you want, Miss Ilmo? Oh, well, I want 5 liters. I want 5 liters of it. So what do you notice I've given you? What do you label this as? M1. Oops, M1. That is stupid. Okay. M1. And then what is this over here? M2, B2. So what am I solving for? B1. So basically I need to figure out how much of that concentrated stuff, how many liters of it or milliliters I need to make this. But I always will have to add water afterwards, okay? Because that's how you dilute something, you add water. All right, so as long as the units of volume are the same, so I'm in liters here, the V1 I solve for over here, what will it be in? Liters, right? So that's basically what I'm looking for. All right, so let's try an example. But for me, this example here has milliliters. It's fine as long as my units are in the same. For volume, we're in good shape. All right, so how many milliliters of a stock solution? What am I looking for? V1, stock solution, I'm going to assign this to be the V1. And I'm asking for the milliliters of 2.00 molar magnesium sulfate. Would you need to prepare 100 milliliters of 0.4 molar magnesium sulfate? So if I give you two numbers as a group, they go together. They're the scenario that goes together. So what can we also go ahead and label? Okay, so what's M1? Okay, so V1 I'm looking for. M1 is 2.00 molar magnesium sulfate. You know what? Nobody cares about who it is. There we go. All right. What else do I know? M2 is 0.400 molar, and B2 is 100.0 milliliters. All right, so I can set this up in the dilution equation I can solve. But just like with our rates of gases, where we're like, oh, you know, hydrogen diffuses at 4 point something times faster than helium, we had to talk about it. We had to say a statement about it. We're going to say a statement at the very end to say how you would prepare it, okay? So M1, V1 equals M2, V2. Divide by what? Dividing by M1 to isolate V1, right? So divide by M1 on both sides. V1 is equal to this, M2, V2 over M1. What's M2? Hold on, 0.400 molar. What's the V2? 100 milliliters. Write your units out, right? Over 2.00 molar. What cancels? Molarity, right? Done, done. We're stuck with milliliters. Great. It asks for milliliters. We're in good shape. I should solve by multiplying and then dividing. So what's that? 40 over, so 20 milliliters. Is that right? Okay. So 20.0, because I've got 3 sig figs. Yeah, 3 sig figs. So exactly 20.0 milliliters of what? What are we looking for? What is this? Stock solution of stock solution. Okay. So now we've got the answer, but now we got to talk about it a little bit. Here's what I want you to say. So the question was, I know how many milliliters. We've actually answered the question, but I want you to tell me how you would prepare it. And this is what it will ask on your test. How? You say your answer, and then tell it what you would do with it. Take 20 milliliters of 2.00 molar stock solution. Give me a second, catch up with me here. And dilute with water until what volume were we trying to make in the end? 100 milliliters, right? Because my V2 is my final solution volume of 100 milliliters. So I'm taking the 20 mils of the stock solution, diluting with water until 100.0 milliliters total volume. It's basically what you're saying. So how much water am I actually adding to this to make 100 milliliters? How much? 80. I'm adding, so I have my 20 of this concentrated stuff I'm starting with. I add 80 milliliters of water to make it to a total volume of 100 milliliters. So draw yourself a picture. Actually, no, I'll have a picture on the next slide. I'll show you a picture of this preparation. Because you guys will be prepping your own solutions tomorrow, and these lovely things. Does this kind of look like a flask?
Yes.
What's missing?
The measurements.
The graduations, right? The measurements. So a volumetric flask has that this appearance to it, kind of a triangle shape. There's graduations on the side that kind of tell you the approximate volume. Don't trust it. Okay, use a graduate cylinder. But this is the king of all kings of all flasks. Okay, this is called a volumetric flask. You only use it if you have to prepare an exact quantity. So if I were preparing, this is a 500 milliliter one. For this one, I would go get to another stockroom. I go get a 100 milliliter volumetric flask. Volumetric flasks have no measurements because you see there's an etched line. Maybe people in the front, there's like an etched line right here. Okay, at that line, it is exactly for this flask 500.00000000000 milliliters. Okay, it is so exact. This thing's probably $20. Okay, a normal Erlenmeyer flask that's 500 mils is probably $5. Okay, the more accurate the volumetrics are, the better quality of solutions you can make in quantities as well. So you get more expensive stuff. Here's my Barbie one. It's a little volumetric flask. Just 10 milliliters. So there's an etched line right there. Okay, that's better than. Here's my. So it's this up. Well, this one's pretty good too. This is my little 10 milliliter beaker. I drink tea out of it. No. So these are the ones we don't really use. Like, how do you use that? Micro scale stuff. But yeah, these are volumetric flasks, and then here's my silver plated one, volumetric. So volumetrics have that funny neck on them, so it's good to know what a volumetric flask is. Okay. Okay. So what we just did is we took a stock solution and we put it in a bigger solution, or we made it a more diluted solution. So here's what you would be doing. You take 20 milliliters of your stock solution, put your 20 milliliters in this empty volumetric flask. As you can see, that was done here. And then what did they do after that? So they took the 20 milliliters of this concentrated stock solution, they put it in here. Then they added water up to the mark, which is exactly 100 milliliters there. So that's your diluted solution. This right here is like your squirt water bottle, so you can get just to the meniscus part, okay? Tomorrow when you make your solutions, if you go over the meniscus, you have to start over. It's very exact science here, okay? So let's try again. Yeah, you guys do this one. This is just like the first one. You do it. It's all you. Take less than 2 minutes. Write down your identities first. Oh no. Don't mind me. Oh, I messed up. 'Cause Oh, you're still not learning. The work is the important part. Write down the statement of how you would prepare it as well. How you would prepare it as well. I'm expecting that you at least set up. Moving soon. Is that what you get? 47.5 milliliters. Who concurs? Fantastic. Okay, who wants to volunteer to tell me how you would prepare this solution? Don't forget, this is 47.5 milliliters of stock solution. How about I do this? Go for it, Ariana. Tell me how to prepare it.
So like take 447.5 milliliters of 4 molar stock solution and dilute it with until 250 milliliters of total volume.
Right, so dilute it with water to 250 milliliter total volume. Good. Okay, so take your 47.5 mils of stock solution, add to a volumetric flask. Now we know what equipment to use, and dilute to a total volume with water to 250 mils. So you would get a 250 milliliter volumetric flask since that was your final solution destination. So I have like every variety back there. So we'll be doing that tomorrow. We'll be making like 5 or 6 solutions. Okay, let's do percent solutions and mass by percents, and then we're done. Okay, this is probably the most writing. Now you can just write down this piece right here if you want to and read the top part, but this is basically, we have a lot of ratios, and I have described that now 3 different ways to express concentration. Concentration is just solute over solvent. This one's just based on the volume versus moles. Just another way to talk about concentration.
You guys wait, my head's pretty big.
So generally, when you have percent solutions, it's usually liquid and liquid, and that's why it's really easy to measure volumes, because if liquids are present, then you just pop them in a graduated cylinder, you got the volume, easy peasy, right? But the liquid that is of smaller quantity, so the liquid that is of smaller volume is going to be considered the solute. Usually the solute is the whatever you have less of. And so usually, I might even say like, oh, ethanol is the solute and water is the solvent. I might tell you more information, but just make sure that if I don't, you can do it yourself. Smaller amount is always the solute. What do you notice that is in the denominator here? Solution, right? Well, what's the solution made up of? Solute and solvent. The biggest mistake people make is they go, oh, this is easy, just percents, right? Multiply by 100 at the end. You just take your solute over your solvent, multiply by 100. That's the most common mistake. What do you hear me say? I said over solvent. That's because, and then problem, I'm going to say, oh, I've got 100 milliliters of this and 300 milliliters of this, and most people go, oh, let's just take 100 over 300. No. What's the total solution in my example I just said? 400. So don't forget to add them up in the end, okay, when you're dividing. That's just an easy mistake to make. Don't put yourself in that stupid mistake category. Okay, so question. What is the percent volume of ethanol in the final solution when 85 milliliters of ethanol is diluted to a volume of 250 with water? So tell me what these numbers mean. Okay, so 85 milliliters of ethanol is the, what do you say? Solute. And then what else do I tell you? I tell you the total solution. So it says a volume of 250 mils with water. So I'm saying ethanol with water is that. So yeah, I'm telling you total solution. Sometimes I'll tell you just solvent and you have to add. So please tell me we are all good. How do you solve this one? Divide and multiply by 100. Good. Sorry, I'm going to finish this up here. If I could work the board. Okay, so 85 mils of ethanol over 250 mils total solution times 100. What's the percent? 34? 30 what? 34%. Cool. Ethanol. Make sure that your units are in the same volumes, right? You can't have liters over milliliters or milliliters over liters. They got to be the same volume. So they cancel. Thumbs up when you got that one. Like I said, some of this is super duper easy. I'll give you guys another second to write. Yeah. Because it says it's diluted to a volume of 250, so it's saying that and that together are 250. The next problem I think I have up here that's separate. Yeah.
So would water be the solvent?
Water is a solvent. Solution though is ethanol and water. Okay, we're good here. So you've seen, and this is, I should show you this before, you've seen this stuff before. You've seen, this is isopropyl alcohol. It says 70%, 99%, you see some that are 50%, but what is it actually talking about? It's literally talking about the percent by volume. So 70% would have how much isopropyl alcohol in it? 70% isopropyl alcohol? Give me an example of that ratio in volume. 70 milliliters of isopropyl alcohol, okay, over what? Mils of solution, right, not water, because it's 70 of isopropyl alcohol over total solution is 70%. So how much water is here? 30 grams, or 30 milliliters of water. Okay, so I could ask you to look at a percent and go backwards, but you guys are probably okay with that. Okay, so last one is going to be percent by mass. So what units do you think we're using? Grams, okay? So a lot of times mass and massing things is going to be because we have a solid. Like you can't pop a solid in a graduated cylinder and go, oh yeah, this is 3 milliliters of sodium chloride. No, that's just not the correct equipment to use for this kind of measurement. So by mass, we always have solid dissolved in liquid, probably. I can easily put some liquid in a beaker and mass that out. That's fairly easy. It's hard to take solid and get the volume of it. So that's why this one's just a different variety. So I may not be questioning this one. This one's simply a mass ratio. Mass of solute over mass of solution. Solution. Solute and solvent. So I could give you an example of salt water. When I say salt water, I mean sodium chloride over sodium chloride in water. That would be an easy example to implement here. All right. I don't think I'm going to do any more example questions. You guys should be able to do 1 through 18 now. Okay? So, if you don't finish, you give the homework. And then if you get done in class, you guys have 25 minutes left right now, 20 minutes left. Get the rest of this done. You'll have very little for homework. I need to start problem set 15, 16 minutes to combine problem set this time. So it's actually short for the fact that it's 2 chapters. Okay? So if you did not finish the Molarity worksheet, that's on you. Yeah. I will. I'll put the answers back up. Write them down if you don't have time to finish them or take a picture or something, okay? So if you guys need to scooch together, work together, please be on task. You have another 20 minutes to work.